Welcome back to another review video. Today we'll be going over recursion. Let's go. So recursion is the idea that an operation is defined in terms of itself. And a lot of times we want to use a recursive solution instead of an iterative solution, because recursive solutions are often more elegant and require less code than their iterative counterparts. Additionally, many data structures are or can be recursively defined, as we will see with binary trees in the near future. And when we talk about using recursion, we're talking about a method calling itself. And all recursive methods should have some sort of base case or base cases, and recursive case or recursive cases. So for base case, a lot of the times this is the simplest output of a recursive method. And this also tells the method when we stop recursing. And for recursive cases, a recursive case will do a small amount of work, however we want to define work, and then it'll hand off the rest of the work that needs to be done to more recursive calls, one or more. And please note, a recursive function can have more than one base case and one recursive case. So we're not limited to a single base or recursive cases. A lot of functions will have multiple base cases and multiple recursive cases, as we'll see with our practice. Let's go over an example. So the Fibonacci sequence is a well-known mathematical sequence, where it will go 1, 1, 2, 3, 5, 8, and so on and so forth. Or the first term, when n is equal to 1, is equal to 1, and the second term is equal to 1 as well. And all the rest of the terms are defined as the sum of the previous term and the term that came 2 before. Or the nth term is equal to the sum of the nth minus 1 term and the nth minus 2 term. So for example, f of 3 is equal to the second term plus the first term, which is equal to 1 plus 1, which is equal to 2. And this pattern continues forever. So the fourth term would be equal to the third term plus the second term, which is 2 plus 1, which is equal to 3. We could write this out iteratively with the following code below, which works for Fibonacci, any Fibonacci term n, ranging from the first term to the nth term. So the 0th term isn't included. If n is less than or equal to 2, we can simply return 1, as when n is equal to 1 or n is equal to 2, we return 1. Otherwise, we need to keep track of the current term or Fibonacci term we're on, as well as the previous term, so we can sum these together. And then, starting with the second term and going all the way to the nth term, we repeatedly sum our current and Fibonacci terms together in order to reach the nth term, and then we just return it. Let's see if we can do this nicer recursively. Here's the recursive solution. It's literally 1, 2, 3 lines of code. So, like with the iterative solution, we return 1 if n is less than or equal to 2. Otherwise, we want to return the sequence, or the nth minus 1 sequence, plus the nth minus 2 sequence. Isn't it clean? This first bit is the base case. So this is the simplest output, and we can simply return 1 when n is equal to 1 or when n is equal to 2, as we know that these terms are equal to 1 and don't have to be defined in terms of previous terms in the Fibonacci sequence. So this is our base case. And a recursive case are anything that's not in the base case, otherwise known as breaking the problem down by making subsequent recursive calls. Because we know the nth term is equal to the nth minus 1 term plus the nth minus 2 term, we can make 2 recursive calls, one for the nth minus 1 term and one for the nth minus term to calculate those as so. And once we calculate the nth minus 1 term and the nth minus 2 term, Fibonacci of n minus 1 and Fibonacci of n minus 2 will return the subsequent terms, and we can return the sum of these two terms to arrive at a final answer. Super cool. And we can break down the process of solving any recursive programming problem into 3 simple steps. The first one is identify the recursive pattern. Try to spot a subsequent recursive call, inside of another recursive call. Or not even the call, but the outputs. Try to find a way where you can define a recursive pattern or see that in our outputs. And we'll see an example of this coming up. Or in other words, it's just looking for recursive calls that contain other recursive calls. And then the second step is we can find our base of recursive cases based on the pattern that we found in step 1. And then third step, profit. because that's it. We just have to look at the output to find the recursive pattern and identify our base and recursive cases, and then code that up. Let's practice. So the problem we have is called write squares. So our task is to write a recursive method called write squares that accepts an integer parameter n and prints the first n squares separated by commas. So for example, write squares of 5 would print all the squares from 1 to 5. So 1, 4, 9, 16, 25. But the pattern is a little different because we want the odd squares first in descending order and then followed by the even squares in ascending order. And here are some more example outputs where write squares of 1 will print 1, and write squares of 8 will print the first 8 squares, with all the odd squares coming before the even squares. And our method should throw an illegal argument exception if past the value less than 1. Cool. Let's see if we can find the recursive pattern. So in this table, I've written out the first 5 calls of write squares as well as their outputs. So write squares of 1 will return 1. Write squares of 2 will return 1, 4, the first 2 squares, with the even square following the first square. And then write squares of 3 will print out 9, 1, 4, as we want all odd squares descending first before any of our even squares. And then this pattern continues. Can we spot an earlier recursive call instead of a later recursive call? Yes, right? If we look at this in terms of recursive calls, write squares of 2 contains write squares of 1, which is just 1, with a comma 4 appended to the end. Write squares of 3 contains write squares of 2, and by the way, WS is just an abbreviated version of write squares. Write squares of 3 contains write squares of 2, but with a 9 comma appended to the front. And then this pattern continues, where, depending on if it's either an even number or an odd number, we'll append a comma and the square of the number to the previous recursive call, or the nth minus 1 recursive call. Awesome. And from here, we can translate this over to a base and recursive case. So the base case is our simplest case. When n is equal to 1, we print 1, and we can stop recursing. How about for the recursive case, or recursive cases? What tiny piece of work are we doing? And what do we hand off to future recursive calls? So one recursive case is if n is greater than 1, because if it were equal to 1, we would hit our base case. If n is greater than 1 and n is even, then we would make a call to write squares of n minus 1, and then a print a comma and 4 in front of that recursive call, or whatever that prints. And the other recursive case, because we're not always adding a comma and n squared to the ends of the nth minus 1 recursive call, is when n is odd and greater than 1. If n is odd, we will first print out n squared with a comma, and then call write squares of n minus 1. And that's everything. Let's code this up. So I kind of just laid out what we said our base recursive cases were, along with our exception check. So the first things first, we want to throw an exception if n is less than 1. So if n is less than 1, we want to throw a new legal argument exception. Great, let's move on to our base case. We said when n was equal to 1, we simply wanted to print 1. So let's do that, print 1. And notice it's not a println because we need all of these numbers to be on the same line. If we use a println instead of a print, then everything after our 1 would appear on a separate line. And this is the case for all of the numbers that we're printing. Our first recursive case is when n is odd. So we can check if n is odd by doing our mod trick. So if n mod 2 is equal to 1, meaning it's not divisible by 2, or there's a remainder after n is divided by 2, then we know for sure n is odd, and we enter our first base case. And also note, we don't have to check if n is greater than 1, because we know if n is not less than 1, and n is not equal to 1, it must be greater than 1. So even though n has to be greater than 1 to reach this recursive case, we can ignore it because it's guaranteed to be greater than 1. And we said if n was odd, we would print n squared with a comma, and then make a recursive call to right squares of n minus 1. So let's do that. So print n squared, n times n, appended to a comma and a space. So we're printing this in the highlighted portion, and then we can print everything after in our right squares of n minus 1 call. Right squares of n minus 1. Awesome, we only have one more recursive case. So we don't have to do an if check here to check if n is equal to, if n is even, or if n is greater than 1. Because like we said, we know n must be greater than 1 by this point, and if n is not odd, it must be even. So we can leave this as an else case. If n is even, we want to basically do the same thing, except it's flipped. For example, if we're printing right squares of 8, we will want to call right squares of 7 first, and then print a comma, space, and then our number. So right squares of n minus 1, and print out our number squared, concatenated to, oh sorry, I flipped it. We want our comma, space, and then append that to n squared. And that should be our answer. Let's run this. Great, let's mark it. We passed all the tests. Yeah, and that's all you really have to do to solve nearly any recursive programming problem. Right, recapping what we did is we went through the output to identify a recursive pattern and found subsequent recursive right square method calls inside of other right square method calls. So we identified the recursive pattern, and then from there it was pretty straightforward translating our recursive pattern into the base recursive cases. Yeah, so hope this review video helped, and have fun preparing for your quiz.